Ladies and gentlemen, esteemed colleagues and honored guests, this is Vincent Queru and I am Adhémar Cohet, and I'm very pleased to present you a science project that was inspired by the work of a French artist born in 1947, Georges Rousse. Who is he? He's a photographer and a plastician. He realized many expositions in the Rhône-Alpes region, and this type of artwork is called anamorphosis. Anamorphosis in art means deformed artwork that are supposed to be seen from a particular point of view. The artwork that inspired our work is located in a temple in the city of Shodoshima in Japan, and it represents a golden circle on a non-planar surface. To create this artwork, Georges Rousse would work with an assistant, and while the painter was standing at the right point of view, he would tell his assistant to paint at the right place in order to create a uniform circle on a non-planar surface. This empirical and artistical process led us to wonder how can we approach scientifically this work, and this led us to the following problematic: how to uniformly light a non-planar surface. Thanks to Manutech-SLEIGHT, the Hubert Laboratory, the Jean Monnet University, and the Institut d'Optique Graduate School, we were able to come up with some answers to that problematic.
So, for obtain a uniform color in a non-planar surface, it's not so easier. So, for start, we start with a simple cases. Cases of two boards of wood. And they are coated with a white paint, and this white paint assured very good reflective qualities to the surface, and we can consider these two surfaces of wood like a Lambertian surface, thanks to the paints. So. For start with a simple case, we take the two boards in a 90-degree angle, and we project just a square with a video projector, a square of a uniform color, and let's see what happens. So the apparent square is not a square; it's just a polygon, and there is a major issue: is the color is not at all continue, and is very shiny in the center, in the intersection of the board. So it's a link with a phenomenon named interreflections. So and it's from the facts like the two surfaces re-emit the light received by the video projectors. And when we are very close, when for a point we are very close from the other surface, the light is re-emitted in the other surfaces, and there is an excedent of light in the corner of the two surfaces.
With our first tries, we've been confronted to two challenges. The first one is the varying luminance. To tackle this issue, we've decided to project, instead of a uniform square, we will be projected a modeled image of a square with its center being darker than the exterior in order to compensate for this phenomenon. And the second challenge would be the shape of the image, because due to the surface being non-planar, we were having non-regular polygons instead of a regular square. To tackle this issue, we have made homemade homemade hand-cut shapes that would compensate this geometrical distortion. The key sources for this presentation include two important theses on the subjects, the one of Dorian Saint-Pierre in 2020 and the one of Rod Adib in 2021. They both gave us the theoretical model of the behaviors of interreflections near the corner. And they also formulated an approach later used by us for the computation and the practical manipulations.
So we use the information from these two theses in order to create a new corrected matrix L from the ideal matrix, uniform colored matrix E0 and another matrix of correction K. The matrix K will take into account all the interreflections. So we create, we can see our two surfaces like two matrices. So we create a new frame of reference, and for each point, each element of the matrix became a point of the surface. And with the data from the thesis, we can compute from every point of the surface what is the extent of light issued from the interreflection of the other surface. So and we can create, we can draw the matrix of interreflections, which can correct the initial matrix.
So our experimental setup was constituted of a video projector and quite obviously, like the board that forms a 19-degree angle. And we've also made an important assumption, the one that the video projector being only 4 meters away from the boards, we would consider that 1 pixel projected by the video projector would be equal to only 1 pixel on the board. The reality could be quite different if we were further away from the board, because 1 pixel projected by the projector could be equal to more than 1 pixel, and we would be obligated to take into account this geometrical distortion. Let me show you our experimental results. What can we observe? On the left, you have the translated figure, the angle being on the right. You can see a darker ray in the middle of the picture. This darker ray corresponds to the computed matrix on MATLAB, and this darker part is the one used to compensate for this phenomenon of interreflection. It being darker compensates the higher level of luminance which is supposed to appear on the corner. On the right, you have the results taken from the right point of view, and as you can see, the shape is corrected because the point of view is the right one, and we are not very far away from the video projector. And you can also see that near the corner, there is no more an intensely varying luminance. We are satisfied with the analysis of the results. We indeed have a uniform square as of the intensity. However, we have 2 points of vigilance. The first one is that we were forced to use green light, as you can see here, because this is monochromatic green light, and using white light, the coating, the white paint coating was not good enough to uniformly reflect all light without considering the wavelength. Second problem would be the point of view. When being further away from the video projector and taking a further away point of view, we would have to take more into account the geometrical distortion. To conclude, by compensating the interreflection, luminance alteration, and fighting the geometrical distortion, we were able to uniformly light a non-planar surface. What we could work on in the future would be changing the point of view, maybe getting further of the video projector. The second aspect we could work on would be work on different shapes. Instead of 90 degrees angle, we could work on more with different angles or more random shapes than only a 90 degrees angle. Thank you very much for your attention. And this is a work of Georges Brousse also.